Electrical solution. Beyond the connections. AC circuit steady-state analysis.
Coming to our first topic, leading and lagging. As we all know, the general form of the sinusoid is V of t equals to maximum voltage into sine of omega t plus theta, which includes a phase angle theta in its argument equation as a function of omega t, and the phase angle appears as a number of radians is shifted to the left earlier in time, as we can all see it in this graph. Lagging is defined by positive theta and leading is defined by minus theta. These two sinusoidal waves, which are to be compared, must in the following 3 points. First, both can be written as sine waves or cosine waves, be written with positive amplitude, and third, each one have the same. There are two types of responses. First, the forced response. Second, the natural response. Coming to the subtopic of the type of responses, that is forced response in sinusoidal steady state. To obtain the equation of a forced response, we are taking a general example of a circuit which consists of voltage and resistor and an inductor. The voltage consists of maximum voltage into sine of omega t plus theta. So basically this is an RL circuit. It is used for the desired force response. So applying the KVL, that is Kirchhoff voltage law, in this circuit, we get the equation is somehow like this: L into di by dt plus Ri equal to maximum voltage into cos of omega t plus theta. So further simplifying this equation, we get the final result of the force response, that is I equal to R into maximum voltage into cos omega t upon R square plus omega square L square plus omega L into maximum voltage into sine of omega t upon R square plus omega into L the whole square. So now let's try one question. The question is, find the current IL in the figure if the transient state have died out. So looking at this circuit, we can see that we can use the Thevenin theorem. So applying the Thevenin theorem, we can see that there is no independent source, so we can calculate RTH by sorting the independent source. So the RTH will be equal to 25 into 100 upon the total resistance, which is equal to 25 plus 100. So simplifying it, we get is RTH is equal to 20 ohm. So now calculating the VOC. VOC means the voltage across the independent source. Voltage is equal to 10 cos 10 raised to 3t into 100 by 125.
Coming to our next topic, that is complex responses and imaginary responses. So now we are going to discuss about complex forcing function and imaginary forcing function. So the basic idea is that sinusoids and exponential are related through complex number by Euler identity, that is e raised to j theta, which is equal to cos theta plus j sin theta. Here j is plus j sin theta. Here j is equal to iota. So talking about complex forcing function, in a circuit which we will assume to contain only passive elements, a current response in some other branch of the network is to be determined, and the parameters appearing in R all real quantities. And in imaginary forcing function, we can construct an imaginary source. It is only necessary to multiply J, the imaginary operator, the fact that our constant is minus Coming to the imaginary forcing function, we are going to construct an imaginary source. It is only necessary to multiply it by J, the imaginary operator, the fact that our constant is minus. Moving further to phasors. What is a phasor? The abbreviative complex representation is called a phasor. For a real sinusoidal current, I is represented as I equal to maximum current into cos of omega t plus theta. So how to express it? Now we are expressing this current, which is equal to I of t is equal to maximum current into angle theta. Similarly for the voltage is represented as V of t is equal to Vm, which is maximum voltage, into cos of omega t plus theta, which we will represent it as Vm into angle phi, which is used in the previous equation we can see.
So till now we have expressed the phasor for voltage and current. Now we are going to express the phasor for the resistor. So for obtaining the expression phasor for the resistor, we are going to take the complex voltage and the complex current response, and accordingly we are going to simplify to get the resistor expressed phasor form. So now let us apply the complex voltage, which is V equals to Vm into e raised to j omega t plus theta, which is equal to Vm into cos of omega t plus theta plus j into Vm into sin omega t plus theta. Now assume the complex current response, which is equals to I of t equals to Im into e raised to j of omega t plus theta equals to Im into cos of omega t plus theta plus j into Im into sin of omega t plus theta. Here Im is maximum current. Also Vm into e raised to j of omega t plus theta is equal to Ri, which is equal to R into Im into e raised to j omega t plus theta. So now converting it into polar form, Vm angle theta equals to R Im into angle theta. It's not an angle. So expressing the phasor form for inductors, for that we need voltage. So the voltage across the inductor is given as Vt equal to L di upon dt. So converting it into complex voltage and complex current, then the Vt will be equals to Vm into e raised to j omega t plus theta, and the current will be It equal to Im into e raised to j omega t plus theta. So putting the values in the equation of the inductor, that is L equal to j omega L, now the equation become as follow: Vm into e raised to j omega t plus theta, which is equal to j omega L into Im into e raised to j omega t plus theta. Dividing the equation by Vm e raised to j omega t, we obtain Vm into e raised to j omega t, which is equal to j omega L into Im into e raised to j theta. Therefore V is equal to j omega L into I. So looking to this equation j omega L into I, we can identify that phasors for inductor I is lagging V by 90 degree. Till now we have expressed phasor form for voltage, current, resistor and inductor. Now we are going to express phasor form for capacitor. So for making a phasor form for capacitor, we need to apply voltage across the conductor, which is given as It equal to C dV by dt. Then converting it into a complex voltage and complex current, we get Vt equal to Vm into e raised to j omega t plus theta, and I will be equal to Im into e raised to j omega t plus theta. Now putting the values in the equation of the conductor, which is equal to C equal to 1 by j omega c. Now the equation become as follow: Im into e raised to j omega t plus theta is equal to j omega c into Vm into e raised to j omega t plus theta. Dividing the equation by Vm into e raised to j omega t, we will get as follow: Im into e raised to j omega t equals to j omega c into Vm e raised to j theta. Therefore what we have derived is I is equal to j omega c into V. So now looking to this equation, the result which we have obtained, we can see that in phasor for inductors, I is leading V by 90 degree.
Comparison of phasor form in devices. Impedance and reactance.
Let's take an example on this topic. Here we need to find equivalent impedance for the circuit given in the question, where operating frequency is given by 5 radian per second. First of all, we need to convert all resistor, capacitor and inductor in their corresponding impedances, as we can see in the figure. Then on observing that 6 ohm impedance is in parallel with minus 0.4 j ohm of capacitive reactance, the combination is equivalent to 0.02655 minus j into 0.3982. Now minus j ohm and 10 j ohm impedances are in series with the above impedances, so the equivalent will be 0.02655 plus 10 j into 8.602. At last, a new impedance which is in parallel with 10 ohm, so the equivalent impedance of the network is 4.255 plus j into 4.929. So this is the equivalent impedance for the given network, and it is the answer of the given question. Nodal analysis using phasors. We will study this topic by this example. Here we need to find time domain node voltages in the circuit. Two current sources are given to us as phasor, and phasor node voltages V1 and V2 are indicated. At the left node, we apply KCL and yield the equation as V1 by 5 plus V1 by minus 10J plus V1 minus V2 by minus 5J plus V1 minus V2 by 10J equal to 1 plus 0J. At the right node, we apply the KCL and yield the equations as V2 by 5 plus V2 by 10J plus V2 minus V1 by 10J plus V2 minus V1 by minus 5J equal to 0.5J. Combining terms and solving the equations, we will be getting 0.02 plus 0.2 j V1 minus 0.1 j V2 equal to 1, and 0.1 plus 0.1 j into V2 minus 0.1 j V1 equal to 0.5 j. After solving the equations, we will get V1 as 1 minus 2j and V2 as minus 2 plus 4j. The time domain solutions in the polar form for V1 and V2 are given by 2.24 angle minus 63.4 degree and V2 as 4.47 angle 116.6 degree. Mesh analysis using phasors. We need to find mesh currents I1 and I2 in the given circuit. First of all, we will convert the circuit in the question to the solution circuit using mesh analysis and phasor transformations. We will apply KVL around mesh 1 and get the equation as 3I1 plus J4 I1 minus I2 equal to 10 angle 0 degree. Applying KVL around mesh 2 leads to equation 4j I2 minus I1 minus j2 I2 plus 2I1 equal to 0. On solving both the equations, we will get I1 as 1.24 angle 29.7 degree, I2 as 2.77 angle 56.3 degree. We will get I1 of t as 1.24 cos 10 to the power 3t plus 29.7 degree, and I2 as 2.77 into cos 10 to the power 3t plus 56.3 degree on converting it into polar form.